Right, let's start then. So our second talk today, we've got Nalini Joshi from Sydney, who's part of the other program that's going on at the moment, Discrete Integrable Systems, who's going to be talking about hunting nonlinear butterflies.
Thank you. I was told in no uncertain terms that this talk had to be accessible. So I hope you'll forgive me for starting with a very simple demonstration. Take two rulers, put one on top of the other. The combined height of these two rulers is the sum of the individual heights of each ruler. That's an example of a linear system. A linear system is one in which the sum of two solutions is also a solution of the same system. But if you stand at a beach and you look at those waves that come up to the beach in the shallow waters just off the sand, then you'll notice that the sum, the height of the interacting waves is not the sum of the individual heights of each wave. In fact, that's a nonlinear system. Whether you're looking at waves on a beach or the larger movements of bison in a plain, on a prairie somewhere, or you're looking at the interaction of black holes far away in the universe looks nonlinear. So the program in which I'm participating focuses on nonlinear systems, but on a particular class of nonlinear systems called integrable. And this is a vast field which has turned out to contain some universal models of science occurring in the field. And what I'm going to do is to concentrate on just one part of it, which is the description of solutions that are highly intricate and highly transcendental, and which turn out to need you to specify initial conditions to infinite order, to an infinite number of digits, in order to specify what these solutions are. I call them butterflies because of the proverbial butterfly effect. I'll come back to that in a moment. But you could call them butterflies also because they're mathematically very beautiful. And I like to think of them that way. So, what is the butterfly effect? You might remember that Lorentz gave a talk in 1963, which is reproduced here, that had this title: Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And from that was born this metaphor of the butterfly effect. That is, that in order to know whether a tornado, or tropical cyclone as we call them in Australia, lands on the coast somewhere in Texas, you need to know the initial state of that meteorological system to infinite precision. And this has become synonymous with chaos, but actually it does occur universally in nonlinear systems. And in particular, it occurs in integrable systems with ordered, non-chaotic, completely coherent behavior. And that's what I would like to tell you about in this talk. I like using this picture. It's an example of a tropical cyclone called Gavin that landed somewhere off the Southwest Pacific in 1997. And I like using it because we had a vice chancellor with the same name who landed around the same time and had a similar effect. So he's not there anymore, though. Okay, so this discovery of chaos in the late 1950s and early 60s, I think, masked for many other people the parallel discovery of completely coherent areas, systems, nonlinear systems. And the prototypical example of such a system is called the Korteweg-de Vries equation, which you might have heard of. And the discovery was made in the early 60s by Martin Kruskal and Norman Zabusky that solutions, wave solutions of this equation, had a particle-like interaction property. And I've reproduced what is called a two-soliton solution of that equation in the graph on the right-hand side. A soliton is a solitary wave, that is an identifiable heap of water, which has particle-like interaction properties, and hence the ending on on the solitary word, And this started off a whole slew of discoveries. In fact, the program that I'm in right now overlaps quite a bit with the other program, the algebraic Lie theory program. And having the two programs on at the same time was either an incredible amount of wisdom on somebody's part or just lucky. It's great to have that overlap here. So in this picture, the front right edge, do I have a pointer? Yes. Is meant to represent time. So this axis is time, increasing to the right. And this axis here is, sorry, that axis is space, and this axis is time. Time is evolving towards the back of the picture. So you can see that as time goes on, this taller heap of water, if you like, or soliton, overtakes the shorter one. They interact nonlinearly in the middle, and then it overtakes that and moves off faster than the smaller one. And if you look carefully in the middle of this picture, you'll see that the two overlapping waves have a height which is different to the sum of the individual heights of those two waves. And this theory, this equation, the Korteweg-de Vries equation, and many others that have been discovered since then, have symmetry reductions, which are called Painlevé equations. They arose in some classical theory around the turn of the last century by French mathematicians led by Painlevé, and they have now turned out to provide universal models of nonlinear behavior. So if you take particle physics and you're looking at random matrix theory that describes the interactions of particles under certain symmetry conditions, what you will find in that random matrix model are probability distribution functions which satisfy Painlevé equations. If you take data that tells you about how long it takes to board an aircraft, under certain conditions, the probability distribution function turns out to satisfy a second Painlevé equation. There are 6 of these, and I'm going to focus on the first of these equations, called the first Painlevé equation, and it's reproduced here. The second derivative of y is 6y squared minus the independent variable x. And in this particular program, we're supposed to be looking at discrete versions of these equations. I don't think I'll get time to talk about the discrete nature, the particular special properties of the discrete versions of these equations, but I hope to show you a couple of pictures right at the end. Okay, so you might look at that equation and say, well, it looks very much like the equation satisfied by a Weierstrass elliptic function. If you have a constant there instead of x, it would be solved by Weierstrass P functions. So what's so difficult about looking at such equations? Well, what is difficult is that the solutions are highly transcendental, and in general, they have an infinite number of poles in the complex plane. So here is a patch in the complex plane where I'm plotting the modulus of the solution of this equation, and the base plane you have in front of you is the complex x plane. These poles, for generic solutions, they're everywhere. You can't go anywhere without hitting a pole somewhere. And they have a further particular feature that they are movable. In other words, if I change the initial conditions of the solutions I'm looking at, the poles change their position. So you can get poles moving apart, poles coming together, depending on the directions in which you move in the complex plane. This is another part of the theory which is extremely interesting. There is a huge amount of complex analytic studies of these equations in terms of the meromorphicity properties called the Painlevé property. Okay, I've told you about the generic sorts of things that might happen. There are very interesting solutions of these equations that have not yet received a huge amount of attention. I just wanted to show you one of those. If this works, there we go. This is a picture, a diagram of what I call the symmetric solution of the first Painlevé equation. It has a pole directly at the origin, and you can see that it's a real solution because you have the reflection property across the real line, and they have this discrete symmetry of the equation embedded in the solution. In fact, the equation is invariant when you change the independent variable by rotation by an angle of 2 pi on 5, and the solution by an angle of, I think it's minus 4 pi on 5. So you can see that there are these 5 sectors or directions, rays, 5 rays of symmetry that you might be able to see in the picture where the poles get slightly sparse. They go on everywhere. This ball you see in front of you is just where the program stopped iterating, and there's a few numerical artifacts that you should ignore. These are not poles close to each other, it's just shadows of poles. So in general, you have the solutions having poles everywhere in the complex plane, but there are 2 other possibilities. So let me show you that schematically by using these diagrams. So here I'm looking at the positions of poles represented by little circles. In the generic case, in the top left-hand picture, you have poles everywhere with these rays of symmetry embedded in them. But if you take a different initial condition at the origin, you can start seeing that there is actually a 1-parameter family of initial conditions in which you get a sparser set of poles in 2 of these sectors of angle 2 pi on 5. And as you approach that 1-parameter family of initial conditions closer and closer, these poles move out to infinity, and you're left with very few poles in the finite region in those 2 sectors. Those were called trunqué solutions by Boutroux, who studied them in 1913. He called them trunqué because if you look in this double sector, there is an axis of symmetry, a bisector, along which the line of poles appears to be truncated. So you have no more poles after a while as you walk towards infinity. Those are 1-parameter families of solutions, but there is an even more interesting solution which you get by taking another limit, and you get to a unique solution which is free of poles in 4 such sectors. And since that means that there are poles only in one of those sectors, and you can have them in any one of those sectors, there are actually 5 of these beasts, 5 unique solutions with the property that you have no poles beyond a certain radius inside 4 contiguous such sectors. And those were called tree-trunqué by Boutroux for the same reason. You've got 3 directions along which the poles are truncated. You might see somewhere in the literature people calling solutions doublement trunqué, doubly truncated, but actually those don't exist. It just means they didn't understand what Boutroux did. Okay, so it turns out that in the physical applications like random matrix theory that I was talking about, this solution of the first Painlevé equation, the tree-trunqué solution, which is real on the real axis, is incredibly important for understanding what's happening in applications like quantum gravity. And one of the major questions that arises is what happens as you walk in towards the origin from infinity. Where do I hit the first pole of that solution? Where are its zeros? And so on and so forth. And that's the question I came to some years ago, many years ago actually now. I first started out looking at asymptotics and then realizing that you can actually get information about the finite plane, the solution in the finite plane, by using the asymptotics as a guide. So where are these types of pieces of information hidden in this picture? Well, before I get there, let me go back to the history of some of the studies that were made on these equations. And I focused here mainly on the first Painlevé equation. So if your name doesn't appear there, please remember I'm only focusing on the first Painlevé equation. Boutroux was the first one who kicked off the asymptotic study of these equations in 1913. Actually, he has 2 papers on the subject, each about 120 pages long. And he won the Baudin Prize of the French Academy of Science with these works. And then you see there's a big gap. And it wasn't until the 1960s that people started picking up the study of the first Panlevey equation again. People like Jablonski, Bartoshevich, Holmes and Spence, they looked at the qualitative behavior of the solutions as real solutions of the equation. And then Jimbo, Miwa, and Sato, and then later Takei and Kawai et al. In Kyoto, looked at it from the microlocal analysis point of view and created some very beautiful theory around it. Okamoto has had a huge amount of impact with his work on studying the geometry of the space of initial conditions. And that's another thing I wanted to mention here. If it wasn't for this program and being able to be here for, I think it's 2.5 months, I wouldn't have met and talked to Dijkstermaat for a whole month in the middle, and that has turned out to be incredibly wonderful experience because I can now understand how that geometric picture marries with the asymptotic picture that I've understood for such a long time. So there are many, many others who've looked at the asymptotics of these equations, but it wasn't until the early decade of this century that we started finding results for what are the finite properties, not the properties way out at infinity, but what's happening in the finite plane. And it was lovely to hear Dubrovin talk about this in a conference a couple of years ago. He's been looking at approaching a catastrophic limit for a Hamiltonian system, and he found that in this particular limit, what you get is the first Panlevey equation, surprise, surprise, and that picture of limiting to the first Panlevey equation needed somebody to supply the information about where the first pole was. And so we were able to give that answer, which is rather nice. So going back to the asymptotics, Boutroux showed in 1913 that there is a transformation of variables that takes you from y of x to u of z, so that the original equation is mapped to this equation for u as a function of z, which makes the asymptotics of the problem much more explicit. If you were looking at this equation, you wouldn't know what was happening necessarily as x goes to infinity, but in this equation, you can see that as z goes to infinity, these two terms in general drop out for bounded u and the first derivative, and so you get an equation to leading order, which is written here, which is of course solved by Weierstrass P functions. So you get elliptic functions as the template, the approximate leading order behavior of these solutions, the generic solutions, near infinity. But there are other limiting cases you can look at. One possibility is that the derivatives are actually smaller than the function itself. And if you look at that possibility, you get algebraic solutions to leading order. In this case, u goes like plus or minus 1 over square root 6, and those actually reflect the pole-free behaviors in the complex plane. So this was the asymptotic picture. How does that marry with the other pictures that I wanted to show you? Well, let's go back and look at the real situation instead of the complex situation for the first Panlevey equation. The equation is at the top of the slide once again. So you can see that where the right-hand side vanishes, where 6u squared minus x vanishes, you have points of inflection for the solution. That's where y double prime is 0. And so you can, if you start with some initial condition, here I've taken y is 1 at the origin and y prime of different slopes. If you take y prime a little bit too large, the solution will blow up almost immediately. You've got poles nearby. But if you don't, if you come back down away from there, you'll see that the solution being convex here stays convex until it hits that upper parabola, then it becomes concave, hits the lower parabola, and then becomes convex and comes back up again. So you can analyze the qualitative behavior of the solutions by looking at this type of analysis quite carefully. There are actually some rather interesting limiting cases here which remain open. There is a godlike solution, as we called it. I hope I'm not being blasphemous here, which comes down and is asymptotic to the top parabola. Then there's a devil-like solution which comes down and is asymptotic to the lower parabola, and there's still questions open about the uniqueness of those solutions, or one of those solutions. So going back to the algebraic expansion in the original variables, you can work out that there's a formal series expansion of the solution. The series is written here. F for formal is the subscript here. And you can easily show that the solutions grow very fast with k. You have not only a factorial, but the square of the factorial in the coefficients, and it just blows up as k goes to infinity. In other words, the series is divergent. It's completely divergent. But nevertheless, the coefficients play an important role in physical applications. In particular, if you look at this, these authors in 1994, you'll see that there are some calculations that they did with these formal series, which is rather important for their application. But divergent series, as Abel said, are the invention of the devil. This is a quote reproduced in Littlewood's preface to G.H. Hardy's book on divergent series. But G.H. Hardy wrote that book in the 1930s, and Littlewood was already saying in that preface that about this field there hung an aroma of paradox and audacity, but that has now been fixed. It's all known now what to do with divergent series back in the 1930s. So what was the problem, and what did they do? Well, these series, the problem with divergent series is, of course, that they can sum to any given number you like, and they might hide free parameters beyond all orders. So that's the major problem that was in the field about 10 or 15 years ago. What's wrong with divergent series? Well, let me show you this very nice example. Take the exponential integral, special function, which is very well known, multiply by x times e to the minus x. That is known to have this divergent series as its asymptotic series when x goes to plus infinity. Okay? It's divergent because of this n factorial in the coefficient of each power. And asymptotic means, as in Poincaré's definition, that if I take the relative error between the function and a partial sum of that series, then that goes to 0 as x goes to infinity. In this definition, n is always kept fixed. N is not going to infinity, it's the x that's going to infinity. Okay? So divergence or convergence doesn't matter in this context. So why do we want to use these asymptotic series if they give us things that are divergent and horrible looking? Well, the thing is that you get very accurate information about the functions by using these series. This function that I've called f has a value which you can work out. You just go to any standard book of special functions. Here I've taken a value, and I forgot to put in the fact that x is actually 100 to get this value, I'm sorry. This is evaluated at x equals 100, and if you take 10 terms of that series, you get something that's very close to that value. It only starts differing in the 17th, 18th, and 19th sort of positions, those positions at the back. These are 20-digit calculations. When you get to 99 terms, you get something that agrees with the result, the known answer, to 20 digits. But if you go too far, say to 281 terms, then the answer is nonsense. So there is a particular part of the series which gives you very accurate information, but if you're foolish enough to think that that game can go on forever, the answer is false. Okay? So there's an optimal point at which you should truncate these series and get the right answer. And that idea led to the theory of Borel sums and led to Écart's theory of analyzable functions, resurgence, medianization. These are words that may or may not be familiar to you, but it led to a very beautiful theory of how to sum these series and to get appropriate information about equations that such functions satisfy. Unfortunately, for nonlinear equations, when you go to the Borel transform, you get an incredible complication. In the Borel transform plane, there is an infinite number of branch singularities. These are the kinds of things I learned at the first program I was at the Newton Institute in 1995. There was a 6-month-long program on exponential asymptotics, and the kind of theory that I'm talking about here were actually developed in that program. So, but my problem is not what happens near infinity. My problem is how can I get information in the finite plane, away from the asymptotic limit? So I needed to do more than Borel theory, because it doesn't actually give me the finite information. So let me go back to that picture. I've got something that's asymptotic to the lower branch of the parabola in the real plane, in the real picture that I showed you before. And what we were able to find was that there is actually a unique solution which has this asymptotic expansion in this sector, the sector of angle 4 pi on 5 above and below the real axis. And it turned out that this is real, it's a real solution. Its interval of existence contains the positive semi-axis. That was already an important piece of information. This function lies below that lower parabola that I showed you earlier. And most importantly, it is monotonically decaying in its interval of existence. And from that point on, we were able to use this information to get information about where the poles and the zeros were of this function. So just to get to this point was an advance. The interval of existence contains the positive semi-axis. That was important to know. But then to work out further properties led us to further advances that we didn't know could be done before. So what did we do? First of all, let me show you a very simple argument. A lot of this is very elementary, but then you have to do analysis that's rather hard to get to the final place. So here's a proposition. Any real solution upon Levé 1 of the y double prime equals 6y squared minus x has a pole on the negative real semi-axis. Let me show you why that is. Well, let's just change variables. Now I'm looking at t, which is minus x. And so because I'm on the left in the x line, t is positive. And so this is the new version of the equation as a function of t. And let the combination of initial data that come in, let me call that capital N. Then because t is positive, it's clear that u double prime is bigger than 6u squared. I can integrate that beyond a point where u prime becomes positive. It has to become positive because the solution is convex by the nature of the equation. So I can multiply by u prime and integrate and still keep the inequality the way it was. And because it's getting bigger, I can show that there'll be a point t1 beyond that point where I can say that this combination of u cubed and n is positive, and therefore u prime squared is bigger than u cubed. Integrate and you'll find that you have a double pole fairly close by. So every solution, even the tree trunqué solution, has a pole on the negative semi-axis. There are many other intermediate results that I could show you. I've just put 2 of them here. So we then started thinking about neighboring solutions. I have a solution that's hugging the bottom parabola. What about solutions nearby to it in the initial value space? We can show that if y is a solution that intersects the parabola, the lower parabola, at some point x naught from above, then it will intersect it again, and then and again and again. If it's a solution that's tangent to the parabola rather than transversely intersecting it, then it will intersect it transversely at a later point. So these intermediate results, they're once again not too difficult to prove. You just take the difference between the lower parabola and the solution, and you can show that the equation is basically oscillatory in the neighborhood of the parabola, and so you get something that's going to oscillate around it as you keep going. Okay, so we then started looking at how to approximate the tree trunqué solution by using that information, and we came up with these things, these objects I call the tangent solutions. tangent solutions are solutions of Panleve 1 with initial data at some point x0 on the right, where the solution is on the lower parabola and is tangent to the lower parabola. So I'm taking something that it's very difficult to plot. If you give those kind of initial conditions, it'll immediately go into the oscillatory mode. But we started looking at this family of functions, and it turned out that that was the right family to look at, because if I take higher and higher values of x0, the point of tangency to the lower parabola, I get convergence to the solution that I called capital Y before, the one that's monotonically decaying and below the lower parabola forever. So here are some numerical results of those functions. So here is the value of the tangent solution, but now at the origin, the value of its slope at the origin. And when x0 is 30, we get these values, and the bold figures are the ones that stay stable as you iterate, as you increase x0 to the right. So that when you get to, say, 30,000, you can start seeing that we've got a fairly large number of digits of accuracy in these results. So these tangent solutions are actually converging to a solution of the Panleve equation. Okay, so how do we find the pole and the zero, the first real pole and the zero of the tree-truncated solution? If I look at the expansion of the function around a pole for the first Panleve equation, you always get this expansion. This is the typical, the only expansion available to you around a pole of the solution. And it has this very nice feature that you start with a double pole and then you skip to a quadratic term, then cubic, then there's an arbitrary constant multiplying the fourth order term. This is actually reflected in the geometry that Okamoto developed. It's very interesting how you see that in the ninth blow-up space as he constructed it, which turns out to be Kodaira's type 2 star surface in his classification of algebraic surfaces. So we're going to be using approximations by these tangent solutions to work out this information, and we have to be slightly careful. Around a pole, we have to regularize the solution, but doing those careful things lead us to the good results. And so what we get is that as these tangent solutions, the point of tangency moves out to the right, we get these results. This is the first zero of the tree-truncated solution, so it's a point somewhere over here. When we saw these first four digits, we thought, oh my God, it's going to be -0.5, but it isn't. There's other digits that come behind that. And this is the slope of the function at that first zero. And this happens to be the first real pole. You can estimate it to any digit you want by using that approximation with tangent solutions. And this turns out to be the value of that arbitrary parameter in the expansion, the C. And in principle, you could take this and work out the other poles that come later in the sequence along the negative semi-axis. So you see, this is why I call them butterflies. These tangent solutions are oscillating way over on the right when you're taking the limit. And that magenta solution that you see there, that's the tree-truncated solution. That's the tornado landing on the left. That's where the pole is in the picture. So this is what we did some time ago, and it has turned out to be interesting, at least to me, and maybe to Dubrovin. Now, what happens when you look at discrete versions of these equations? And here I only have questions, not answers. I've got the initial Panleve equation here, and this is one integrable discrete version of that equation. There are many, including Q difference equations. If I look at this equation as n goes to infinity, okay, what I can do is to consider the qualitative analysis of these solutions. And in fact, you can find a Boutroux type transformation here. The x's grow like square root n, and you find that when you do the right scaling, the solutions are given to leading order by elliptic functions. Once again, what you get is the addition theorem for elliptic functions to leading order. And this is a picture I drew of what happens on the complex sphere. I've taken the x-plane. This x is here the solution, not the independent variable, remember. And I've wrapped it up into a Riemann sphere, the complex sphere, and I'm looking near the North Pole in this projection. And you have solutions that start off iterating from initial values somewhere down here. They start iterating, so the yellows are the earlier iterates. They come near here, and then they go to the other side of the North Pole, come back, and then they go around here. And as the color changes from yellow to green to blue to magenta, you're getting closer and closer to that North Pole. And that reflects the scaling, the square root n scaling that you get in the Boutroux type explanation, description of this equation. And so you can see that what's happening is that, similar to what was happening in the continuous situation, as you walk along some path, you're going to go close to a pole and then be finite, and then close to a pole, then be finite, close to a pole again. And that's exactly what's happening here. You're walking along a fence with poles sticking up every now and then nearby, and that's why you're going close to the North Pole and then coming back away again. So that was not too difficult to explain, but there are also truncae type solutions in these examples, in these discrete equations. Here is one picture that suggests that kind of solution. We've got, remember, the truncae type solutions were things where the poles became sparse in two sectors, so if you're walking in there, you won't necessarily be near the poles, depending on the direction in which you go. And here is where you're starting to iterate. You iterate from here to there, back again, back again, back, back, back. And then slowly you go towards the North Pole, but you don't go near it in your travel, in your intermediate steps as you iterate. So what's happening here is something that is pole-free, something that is more algebraic in behavior in the power series expansion, and you can also get those kind of power series for the solutions with this kind of behavior. But of course, the questions about global description, what happens to these solutions if I'm coming back away from infinity in order to try and guess where the solution zeros and poles are, those are completely open. And what we're doing here in this program is, I guess, trying to tackle all of those types of open questions. So I think I'll stop there and let you get to your wine reception. I wouldn't want to hold you up. So just to summarize, the Painlevé equations and, in fact, integrable systems are important in various bits of science. In fact, they come up as universal problems, as I said. There are physically interesting solutions with very subtle and intricate behavior. The finite properties haven't received as much attention as the asymptotics, and I think they deserve as much scrutiny as any of the favorite special functions that you might have learnt about as undergraduates. Airy, Bessel, Whittaker, hypergeometric, elliptic, theta, all of those functions are very well known now, but the Painlevé equations are still waiting in the stables for better description. And what I've done in this talk is just to describe a very small sliver of what we know in this field for the first Painlevé equation. And as I said, the properties of these discrete Painlevé equations remain an open question. Right now, we're looking at the structure and the properties of the equations rather than individual properties of the solutions themselves. And that's to come. The next program, perhaps. Thank you.
Thank you very much. So do we have questions?
I think you mentioned that this truncae solution is free of poles in 4 out of 5 sectors, but
That's
I thought that it's de Broglie conjecture which still to be settled.
That's for the fourth order case. The second order one.
No, just Painlevé one. Is it known? I mean, the tritron
Yes.
K is free in, and who did this?
Oh, you mean in the complex?
In the
Yes.
complex plane.
No,
in
that's
co-
not done. That's
It's not done.
done. This is still an asymptotic result, not
Right.
known for the remainder of the finite region of the sectors.
But I think Dubrovin conjectured that it is true
Yeah.
actually
Yeah.
everywhere.
In fact, Boutroux conjectured too. But
Boutroux,
yes, I think so. Yes.
but it's still
yes,
not known.
everybody believes it, but there's no proof.
I think I should have asked this question before this program was actually selected. I mean, when you take an, if it's too late, then it's fine. When you take an equation and discretize it, there are many ways of discretizing
That's
it.
right.
And so I'm not clear what actually qualifies as a discrete integrable system. So if you go back a couple of charts,
Yes.
and you go to the one where you had dP1,
Yes.
I couldn't actually easily see why that was a discretization actually of P1.
Right.
And why is that particular discretization so special? Can you say a little bit about what identifies a
Yes.
DIS?
Sure. I think the shortest answer is what characterizes integrability in the differential equations is inherited by these discrete equations. And to me, what characterizes integrability is that these nonlinear equations are solved through associated linear systems for which they are the compatibility conditions. These are called lax pairs. And these discrete integrable systems also have that feature. They can also be solved through linear problems that they are associated to, for which they are the compatibility conditions.
So just on a simple question then, why, I mean the notation is slightly different. X, Y goes to, N is like
Sorry.
X. I think the notation is
Yeah,
different.
I'm sorry, the notation is
Yeah, so
confusing.
I got that far.
X is
but
like-
I couldn't actually, even with that spectacular insight, I couldn't actually see why the right-hand side qualified to be described as a discrete form of P1.
Right. What you need to do is to think about this for, how can I put it, the continuum limit. Do you know what I mean
Sure,
by the
yeah, no,
continuum?
I'm
Right.
with you on that.
So-
and with that as a
so if you
second
take-
derivative, etc. Yeah.
Right, so if you take these iterates expanded in Taylor series now, what you will
Absolutely.
find is that you have to scale these quantities, the A's and the B's and the C's as well. And you will see that there is a situation where the leading terms cancel. So,
But why is there a 1 over xn on the right? Just to show I'm really looking at it.
well,
Because that's like having
Yeah.
a 1 over y on the... See, the left-hand side is sort of y double dash plus
Yes.
y.
yes. But when you take the limit, you are actually going to expand around a finite value, a constant value.
Ah,
And when you do that, and you bring up
Oh.
positive powers in the Taylor expansion
okay.
on the right. That's right.
One question. You said that these are applied to various bits of physics.
Yes.
Could you just give us 2 sentences about what particular parts of physics?
Okay, if you take, as I was mentioning, if you take particle physics, a long time ago Wigner decided that there were so many different types of particles and interactions in fundamental properties of atoms and so on, that it was better to represent the interactions between particles through very large matrices with random entries. And so long as the matrices represent the symmetries, properties of those particles, then you should be able to get some macroscopic information about the particle interactions from the properties of these matrices. The eigenvalues, the various other information about spacings of eigenvalues and so on. And if you take that random matrix picture now and consider the partition function, as they're called, or probability distribution type function, it turns out that they satisfy Panleve equations. Don't ask me why, it's a miracle of some kind, but this is true for all of the types of random matrices that people normally study. Orthogonal matrix ensembles, Hermitian matrix ensembles, and so on.
Right, well, let's thank Professor